All right, good morning, everybody. So welcome back to Engineering 250. We're wrapping up week 7 today. So any questions to start with? You're finishing up your homework 5, I believe. We're going to go over homework 6 today. Yeah, go for it.
Could you draw a state transition diagram?
Sure thing. So our goal with analyzing state machines is to understand what the machine does. And generally speaking, these machines are boxes. There's some kind of clock, which is an uninteresting pulse train that just feeds in. And then there's some set of inputs. And the line on that arrow, remember, means, it could be more than one arrow, but I'm not going to draw, 12 arrows. So that's called a bus. So that's a collection of one or more inputs and one or more outputs. And the goal of analyzing this machine is to understand, hey, based on what the inputs are, what happens to the outputs? And that usually involves understanding what state the machine moves from. So you go through this whole process that we've worked through a few times of making this state transition table. And so suppose your table comes up like this. So I'm going to do PS for present state and in for input. And let's just suppose you have 4 states, and I'll just call them A, B, C, D. And your input, let's just say it's a single bit. And so it could be a 0 or it could be a 1. And so we have an output, which, I don't know. It's random. And then we have a next state. And let's say, our next state is all right, totally made up. So a state transition diagram is a visual way to sort of see this without having to think about it as a table. It shows the flow from one state to another so that we can sort of get back to the original machine and address the question, hey, as the clock ticks, how does the machine change over time? So you've already decided in making this table how many states you have. And for this example, we're supposing 4 states. So you can write these down, however you like. And sometimes the way you write them down is not a good way because you end up with lots of lines crossing each other. And so you might draw this a few times. In this case, the output depends on both the state and the input. For example, in state A, the output could be a 1 or it could be a 0. So if the output depends on the inputs, that's called a Mealy machine. And in a Mealy machine, we're going to draw our arrows like in/out. And we're going to have our state. If the output only depends on the state, if every time I'm in state A, I have the same output, if every time I'm in state B, I have the same output, and so on, that would be a Moore machine. And the only difference is, since the output is independent of the input, we can list the output for a given state, because we know it's always going to be the same for that state, and so our transition arrows just show the input. So just looking at these first rows for state A, I can see the output depends on the input. So this is going to be a Mealy machine. So I'm going to put my key up here, which is going to say inside my circle I've got the name of the state, and then on the arrow I've got the value of in and the value of out. And now we just start drawing arrows. If we're in state A and our input is 0, we're going to go to state B. So state A, input of 0, we're going to go to state B, and our output here is going to be a 1. If we're in state B and our input is 0, we're going to go to state B with an output of 0. So state B with an input of 0, we're going to output 0 and stay in state B. C with an input of 0 will go to A. And in that case, the output will be 1. And then D with an input of 0 will also go to C with an output of 1. So D with an input of 0 will output 1 and go to, oh, this should go to state C. And we can finish this up since we started it anyway. If your input is a 1, A goes to D. And the output there is a 0. If you're in state B, you go to A. If you're in state C, you go to D. And the output there is a 0. And if you're in state D, you go to B with an output of 1. So there's your state transition diagram. And so now you can see a little more clearly sort of, if you begin in state A, what happens? Well, you could go down here and come back here and go there, or you might come here and flip back and forth between these, or you might get to state B and flip here and so on. And since it's kind of a random circuit, there's no sort of higher level interesting behavior happening. But in some cases, this makes it more clear what the goal of the machine is, what its behavior is. So someone said in chat, if you have an equation, z equals a bar x, and if you really meant that, right, then z is always going to be 0 because a and a bar is always false. So z is just 0. So I mean that would be a Moore machine for sure, because it wouldn't even matter what the input was or what the state was. So I could draw all of my states and just show a 0 down here. But that's probably a sort of dysfunctional machine. The z doesn't really depend on the states or the inputs. It's not really a part of the machine in some sense. But yeah, I would call that a Moore machine if that's what all the outputs were. But it's really inputs that we think of as being Mealy or Moore. But if all the inputs are Moore, then it's a Moore machine. If all the inputs are Mealy, it's a Mealy machine. Sometimes it's a mix. Yeah, you're welcome.
Yeah, I had a question about the key for the Mealy or Moore.
Mm-hmm.
Thank you for covering that.
Yeah.
Also on question 4, sorry, on the homework, the actual J, it looks like the Z output, Z0, it's like coming out of the J1 and Q bar 1. I'm not really sure where Z is coming from.
So when you have a picture like this, you have to kind of do some maze running, and if you know that this is an output, it can be connected to multiple points, but only one of those points should be driving it. So J is an input to a flip-flop, so that's not actually supplying a voltage, that's taking in a voltage. But the XOR gate, this is the output side of it over here at the tip, that's what's actually generating the signal. So this is the equation you would write that gives you what Z0 is. And then J1 would also be equal to that.
Alright, perfect, thank you.
And sometimes, more complex circuits, you end up chasing this, 5 different ways before you eventually get to an actual output. All right, other homework questions?
Yeah, actually.
Sure, go ahead.
How many states can you have? So on this one that you're showing right now, you have 2 JK machines. Does that mean it's 4 states?
Yeah, I have 2 flip-flops. And so if you have a single flip-flop, your output can be a 0 or a 1. If you have 2 flip-flops, each of those can be a 0 or a 1. So the combinations of those are 0, 0, 0, 1, 1, 0, or 1, 1. That's 4 states. If I had 3 flip-flops, right, I could have a 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, right? You'd end up with 8, or 2 cubed states. So generally speaking, 2 raised to the number of flip-flops tells you how many states you could have in the machine. All right, how about Lab 6? Any questions on how you're going to do your final version of the traffic light controller? Well, let's see. If output Z is not dependent on state or input, how would you draw it in a diagram? It's almost not a part of the state machine, right? So I mean, you could almost make a note, C2 equals 0, or you could put it in the state circle and just list that same unchanging value in each state. But if it's not dependent on the state and it's not dependent on the output, it's almost like it's part of a different circuit. So you could just note its value on the side, or if you wanted to put it in the diagram, right, just say I'm going to put the value of Z0 here and then put that value in each circle. Cool, you're welcome. All right, questions on the lab? So we talked about Lab 6 on Monday, and it's a 2-part lab. The first part, you're building a delay circuit, and we talked about how to design that, how to test it, and then how to write it up in your lab. And then part 2, you're using that delay circuit to implement your yellow light. And I suggested an approach very different from what we're going to do today with general state machine design. There's a trick you can use by taking the old green signal from Lab 3 and running it through your delay circuit, and then doing some logic on the original and the delayed version of that old green to generate your 3 lights. And I think once you design that and build it for one lane, then it becomes pretty clear how that works, and then you just replicate that work for the other 2 lanes. All right, let's talk about state machine timing. Because everything we've done so far is theoretical. We have perfect flip-flops. They always do what they're supposed to do. And we haven't really said anything about, you know, this pulse train that's going into our system. We haven't really said anything about the nature of that. It's just, you know, 1 0 1 0 1 0, yes no yes no. And that's used to drive the transitions of the flip-flops from one state to another. So in a typical machine, every time that the clock ticks, the J and K inputs in this case are sampled and the Q outputs change according to what a JK flip-flop does. If these are both 1s, Q will toggle. If it's a 1 0, Q will set. If it's a 0 1, Q will clear. And if these are both 0, nothing happens. Q stays unchanged. And so that's fine in theory, but in reality there's a limit to how fast you can change these flip-flops. And that speed limit is a function of what we call the setup and hold time. So if these are our inputs going into the flip-flop, so we're just thinking about one flip-flop like a D flip-flop or a JK, and here's your clock. And this is something that's positive edge triggered. We know that at this point, the stuff inside the flip-flop basically looks at the inputs and decides what to do. And so your inputs, you know, they might change, they might be high, they might be low, and so on. But there's some period of time around the clock tick during which things have to be stable. And so this time before the clock tick, that's called the setup time. And the time that things have to be stable after the clock tick, that's the hold time. And so we'll sometimes write this with tau, Greek letter T, with a subscript SU for setup, and this is tau with a subscript H for hold. And the whole deal is just this, right? Suppose I want to input a 1. So my input might look like this, right? It's got to be a 1 before the clock ticks. I can't have it be a 0 0 0 0 0 and then the clock's about to tick and I'm like, oh, I want a 1, right? It may not work. So I have to have that input at its given value, you know, a little bit before the clock tick. And I also have to keep that value a little bit after the clock tick. As soon as the clock ticks, I can't just say, okay, the clock ticked, I'm done, I'm going back down to a 0. So one way to think of this is imagine taking a vote by a show of hands. So somebody says, okay, should we have a final exam or should we have a cookie and ice cream party, right? Raise your hands if you want cookies and ice cream. And the teacher starts going around the class counting hands, right? Well, you've got to keep your hand up a certain amount of time after the clock tick, after the teacher says, you know, show me your hand, right? And begins counting. And so that would be like the hold time, right? When the teacher says raise your hand, you can't just put your hand in the air and put it back down because it takes time for the circuitry, right, the teacher to register those inputs. Yeah, I've got my hand raised too. So that's what the hold time is like. And the setup time would be like, you know, you need to raise your hand before the teacher looks at you to see if your hand is raised. If you raise your hand at the exact moment that the teacher turns and looks at you, well, they might look at you before your hand is all the way up in the air and say, oh, you know, this person wants a final exam instead of a party. So that's the setup time, right? The clock event is when the inputs are going to be sampled, and you need to just have those inputs stable before and after that moment. Because the flip-flop is a physical device, it takes time to do its thing. So these are the characteristics that limit the speed with which we can clock a state machine. These are some of the characteristics. So let me show you this general picture again of a state machine. We've got some sort of memory. These are our flip-flops. And we've got the outputs of these going into some kind of combinational logic. That's, you know, the XOR gates and the inverters and all that stuff that we see outside the flip-flops. And then we have some set of outputs. And the outputs go back into the memory. And maybe there's some inputs. And there's some outputs being generated somewhere. But we're mostly interested in the transition from state to state, right? If the outputs take a while to settle, that's a different issue. But looking at this movement from state to state, and there's a clock feeding the system. So here's the question. If the clock ticks, then the flip-flops will begin to change state, right? The inputs get sampled, the outputs eventually respond, and then those changed outputs feed this combinational logic, and the output of that combinational logic comes back and feeds the inputs of the flip-flop. So let's just look at a specific example. So, right, homework question. So here's an input, right? It goes through some combinational logic. In this case, it's just one gate. The output of that feeds the D input. The output of the flip-flop goes back into this combinational logic. So this is a simplified version of this. Right, where the combinational logic is just our AND gate. All right, so how fast can we click this? Well, when the clock ticks, the following things need to happen. The output here needs to be set to whatever the current D value is. And since that output might change, that new value has to get through this combinational logic. And then the output of that combinational logic has to go back into this D input. And if we're going to make this machine work correctly, we can't tick the clock again until the output has changed, the output of this combinational logic has settled, this D input has been given its new value, and we wait for the setup time. And so we can start writing equations to figure out what the timing constraints are on this and what the maximum speed of this circuit can be. So the memory, we just kind of think of having two parameters, a setup time and a hold time. And the combinational logic has a propagation delay, which we can just think of as tau PD. That's the propagation delay. And propagation delay is the answer to the question, if I change an input, how long does it take for the output to be correct? And if I have, you know, a simple inverter, and I change my input from a 0 to a 1, we know that the output takes a little while to change from a 1 to a 0. 3 or 4 nanoseconds maybe. If I have an inverter going into an OR gate, going into an AND gate, going into an XOR gate, going into a MUX, going into something else, how long does it take for this output to respond to a change in input? Well, I don't know. It's more complex. But it might be, you know, the length of this propagation delay plus this delay plus this delay plus this delay plus this delay. And so finding that propagation delay is a hard thing. What you can usually do is you can find a worst case. And worst case, if I have a chain of, you know, these 5 input going into output, which goes into an input, which makes an output, and so on, I can just add up those propagation delays. But that may be a longer delay than I'll actually ever see. But we're looking for, you know, what's the the fastest we can guarantee that this output will be correct after we change an input. So when you're told that a inverter takes 3 nanoseconds to change, that's worst case. Could be it changes in 2 or 1. So tau PD, the propagation delay, that's our worst case time from a change in an input to a change in the output. And so let's imagine our clock, and it ticks right here. And when this tick happens, our outputs change, and they start to go through this combinational logic, and we have to wait that amount of time, right? Whatever the propagation delay is on this combinational logic. And after that amount of time, the inputs to your flip-flops should be stable. And once those inputs are stable, now we have to wait a little more time, the setup time, to make sure the flip-flops don't misbehave. So the clock ticks, we wait for the propagation delay for the outputs to stabilize from here, and then we wait for the setup time to give the circuitry and the flip-flops time to digest those inputs, and at that point, if we wanted to, we could tick the clock again. The hold time usually doesn't matter. Why doesn't the hold time matter? Because the hold time is usually, a few nanoseconds, and the hold time is saying, hey, you have to wait at least, some amount of time after the clock tick before you can change those inputs. Well, generally the hold time is a lot less than the propagation delay. So it might be, this much time here. So we don't usually have to worry about that because this combinational logic is going to take a lot more time. So the total time from clock tick to clock tick is just the sum of the propagation delay and the setup time. So here's some fictitious numbers. So suppose we have a set of flip-flops and the setup time is 35 nanoseconds. And the hold time is 10 nanoseconds. And suppose our combinational logic has a propagation delay of 15 nanoseconds. So propagation delay is going to be 15. Setup time is going to be 35. The minimum time from one clock tick to another is going to be 50 nanoseconds. So if I tick the clock at time 0 and then I tick it again 10 nanoseconds later, that's too soon because my combinational logic hasn't even finished calculating its outputs based on these new inputs. And if I tick my clock after 20 nanoseconds, well, these outputs have been stable, but, only for 5 nanoseconds. So it took 15 seconds for these outputs to stabilize. If I tick after 20 nanoseconds, these inputs have only been here for 5. And so if I want my circuit to behave correctly, I have to wait the 15 nanoseconds for the outputs to stabilize. And then once those outputs, which are inputs to the flip-flops, are there, I have to wait my 35 nanosecond setup time. So that's a total of 50 nanoseconds. And yeah, if the hold time was longer, then we would definitely take it into account. But for 10 nanoseconds, it's fluff. All right, so what we're calculating is the minimum time between pulses. So whatever our clock does, this has got to be at least 50 nanoseconds. All right. If we take longer to tick our clock, that's totally okay. Right? You can clock your circuits from lab 5 using a push button. And you just push the button every few seconds and the counter counted up by 1. There's really no practical maximum time for this clock tick. But we're calculating what's the minimum time between clock pulses, and in this case it's 50 nanoseconds. All right, well, so when you have a signal, and it doesn't matter if it looks like this or it looks like this, or it looks like this, right? For any of these, we can talk about the time from one pulse to another pulse, and this is called the period. So the period of a signal is how much time it takes for that cycle to repeat. And I could do it, from the rising edge to the rising edge. That would be the typical case if our circuit is, positive edge triggered. Or I could do it from a falling edge to a falling edge. But if it's a periodic waveform, right, I can pick some point and see how much time it takes till I get to that point again. That's the period, right? That's an amount of time. And that's what we can calculate directly using these kinds of analyses, right? So in this case, adding together the setup time and the propagation delay. But what we're usually interested in is frequency. And frequency is the reciprocal of the period. And so this is where it's easy to get kind of tangled up with units and reciprocals and things like that. But let me show you the way I learned to think about this that I think is pretty easy. So we just did this analysis and we decided our period was 50 nanoseconds. All right, so period, and that's sometimes an uppercase T, is the period, is 50 nanoseconds. Well, it's actually 50 nanoseconds per cycle, where a cycle is, one repetition of your waveform. So 50 nanoseconds per cycle. Well, frequency is just one cycle per 50 nanoseconds. So the frequency is saying that our waveform changes once in 50 nanoseconds. And usually we express frequency in, number of cycles per 1 second. That's what we call a hertz. So if we have one cycle in 50 nanoseconds, how do we convert that to something per number of seconds? And so this is where we get into all the business with units. So I can say, 10 to the 9th nanoseconds per second. And then we do this thing that I think physics teachers hate, but it works really well. We just cancel our units, right? And so our frequency is 10 to the 9th divided by 50 cycles per second. Or 10 to the 9th over 50 hertz. And hertz just means cycles per second. So what's 10 to the 9th over 50? Well, it's the same as 10 to the 8th over 5. which looks like 2 times 10 to the 7th. Because if I do 2 times 5, that'll be 10 times 10 to the 7th, that'll be 10 to the 8th. Or, you know, you pop it into a calculator. Well, 2 times 10 to the 7th is 20 times 10 to the 6th. And 10 to the 6th is my mega multiplier. And so this is 20 megahertz. So certainly if you're doing a question like this on an exam, or, you know, I reassigned this question for homework 6 because I said to skip it in homework 5. What you really want to be sure you've got written down very clearly where your teacher can see it is this kind of calculation here, where you figure out the period and you show that it's the sum of the propagation delay and the setup time, and you get that. And then if you make, you know, some sort of mistake in there, if you add 15 and 35 and you get 60 by mistake, right? That's just a math error instead of a conceptual error. And certainly going from here to a frequency, right, you want to make sure that it's clear that this was the period, and then if, you know, a multiplier goes off or something like that, well, that's just a math error. I'm not too worried about that. But in this case, here's our punchline. This machine can run at a maximum frequency of 20 megahertz. Right? It's a simple machine. It's some flip-flops and a bit of logic, right? But it's speed limited. The fastest we can run that clock is 20 megahertz. So your frequency is 1 over the period. And we commented that the period could be longer than 50 nanoseconds. It could be 5 days, right? But if you tick the clock once every 5 days, your frequency does what? Does it get longer or shorter, bigger or smaller? It gets a lot smaller, right? And that's, you know, the bigger you make this thing, the smaller you make that thing. So our maximum frequency is 20 megahertz. Our minimum period is 50 nanoseconds. So minimum period is 50 nanoseconds. Max frequency equals 20 megahertz. So that would be your final timing analysis for that circuit. So, question, what are the things that happen if you exceed the maximum frequency? What if I tried to clock this thing at 22 megahertz, or 25 megahertz, or a gigahertz? What kinds of things do you think happen? Yeah, so all good answers. So the first thing we're going to observe is unpredictable behavior. Output signal being unreliable. Because, you know, either we'll be latching values into our memory that aren't correct because our combinational circuit hasn't had time to respond, or, you know, we might get into that weird Tinkercad mode where we are changing the inputs at just the wrong time, and our memory starts to oscillate, right? Which a simulation usually has a hard time with, but for us, you know, our output might start doing something unpredictable. And so the first thing you usually see when you begin to overclock a system is incorrect behavior. And so if you ever played with overclocking a CPU, you run, you know, Quake in the background or something, and you start cranking up the clock speed, because these clock speeds are usually software controlled. And so by just loading different values into registers, bless you, you can start driving up the clock. And your machine that you got that said it was a 2.4 gigahertz machine, well, you can run it at 2.45 gigahertz and see what happens. And when you first start doing that, probably it's still going to work correctly. Because when you sell a machine and you say this is a 2.4 gigahertz CPU, you're guaranteeing that CPU will work at 2.4 gigahertz. Well, I would not guarantee this circuit at 20 megahertz. I would guarantee it at 15 megahertz, right? So you put a little headroom in there to say, hey, you know, if something changes, if this machine is running in a cold environment and this setup time is a little longer than I thought it was, right? You don't want the system to misbehave. So you usually put some wiggle room in there, and so if your analysis says this is the maximum frequency, you would probably sell this as a 15 megahertz circuit. So when you first start to raise the frequency, chances are things will still work. But at some point, you'll start seeing your circuit misbehave. And, you know, depending on the luck of the draw, your chip may be spec'd out for 20 megahertz and they sell it as a 15 megahertz, but it may be that the physics, the exact dimensions and placement, and the semiconducting characteristics of the way these components were manufactured on that given day, it might run at 30 megahertz, right? It's just not guaranteed. But at some point, the clock will get too fast for the circuitry, and you start getting incorrect outputs. Now, if you keep increasing the clock speed, and this could happen before you reach that type of failure, but somewhere along the way, bye, have a great day, see you after school. Somewhere along the way, as the clock speed increases, then you start getting into physical effects along the lines of heat. Because the faster you try to change the state of these circuits, the more heat is produced. And so somebody said explosion. And yeah, you can start generating smoke from your chips. And so you can go on YouTube, you can look at, you know, extreme overclocking videos and such, and people will just crank the clock speed up slowly on a Pentium processor until it starts to smoke and in some cases burst into flames. And then obviously, you know, your part has been compromised. And so one thing people do is they try to improve the cooling of their chips. So if you can take that heat away from the chip, you can possibly, you know, avoid having it smoke and fail. And so you can, you know, increase your fan speed, increase the number of fans. You can start water cooling. You can start using Freon, or, you know, if you're going to put it on YouTube, liquid nitrogen, and try to take away that heat, or you know, deal with the effect of that heat. Liquid nitrogen doesn't really wick it away, but it cools it and lets you get the clock speed up a little higher for a few seconds. So that's one way that these limitations come into play, right? Is from just these propagation delays. But there's other things that kick in later, such as, you know, the fact that you generate heat when you change state. And sometimes you try to overclock and your circuitry can keep up, but the temperature goes up too high and your chip, you know, fails physically and permanently before you get to this point where the outputs are misbehaving. And so that's a fun pastime if you've got money to spend blowing up chips. All right, so that's a first order analysis, and in practice, you know, we don't design these machines by hand. We do that now, and we do that this coming week, so that we understand these machines and we understand the nuances of designing them. But then eventually we write software programs that do this design for us, and part of those programs include timing analysis. And it will do, you know, a typical timing analysis, a worst case timing analysis, and so on, and tell you, you know, what's the maximum frequency, and so on and so forth. All right, so on the homework that you're turning in today, I said to skip question 5, and then on homework 6, I said go ahead and do question 5. So here's question 5, right? Setup and hold time. Propagation delay for combinational logic. What's the maximum frequency? Show all your work and explain your answer. what happens if you clock the system faster, what if you clock the system slower. So we've kind of talked around those already. So that's a pretty kind of straightforward set of calculations. All right, questions around any of that? Alrighty, let's go ahead and take a 5-minute break. And when we come back, let's start talking about state machine design. How do we synthesize a design for a state machine based on what we want the machine to do? So we're going to run the process we've been doing in the reverse direction. We're going to start with a state diagram, turn that into a transition table, turn that into a set of equations, turn that into a circuit diagram. So we're going to come up with a machine based on the behavior we want, as opposed to here's a machine, tell me what it does. So we're going to do the synthesis part of this process. So we'll come back in 5 minutes and we'll talk about that. All right, so I'll see you in a few. All right. Let's let's do state machine synthesis. So our goal is to reverse the direction of what we've been doing for the past couple of weeks, to start with an idea of what we want a machine to do, and then figure out, you know, what kind of flip-flops, what sort of combinational logic do we use to build a machine that if we analyzed it would produce that state diagram. So let's start with a diagram like this. And I'm gonna have one more output, MOORE, which I'll call Z, and I'll have an input X, which I'll call Go, not X. And here's what my machine's going to do. I'm going to start in state A. State D is going to output a 1. My other states will output a 0. And if my go input is a 1, I will move from state A to state B, to state C, to state D, and I will stay here in state D forever, as long as my go input is a 1. If my input is a 0, I'm going to go back to state A. So the effect of this machine is, you know, it's something that has a 2-bit counter, basically. And as long as I make my input equal to 1, it will move from state A to B to C to D, and when it gets to state D, my output will be a 1, and it will stay there forever. But at any point, if my input is a 0, I'll jump back to the beginning, to state A. And I don't intend to do anything particular with this machine. Again, it's just an example, so there's no deeper meaning here. So our analysis is comprised of the following steps. Step 1, how many flip-flops should I use in my design? So I have a total of 4 states. Can I build this machine with just a single flip-flop? Is that possible? Right? I can't do it with just one flip-flop because a flip-flop can only record 2 things. So I'm going to need at least 2 flip-flops. And I know if I have 2 flip-flops, I can record 4 different combinations. So 2 flip-flops would be sufficient in this case. I could design it with more than that. I could use 4 flip-flops. I could throw in 50 flip-flops if I wanted, but there wouldn't be much point in that. So I'm going to go with the minimum number, and I'm going to use 2 flip-flops. Alright, so the next question is, what kind of flip-flops? Well, we've seen, you know, from homework, we can use D, we can use T, we can use JK. We could use a combination. We could use a D flip-flop and a T flip-flop. There's nothing that necessarily constrains what types of flip-flops we use for a design. But, you know, of course, in some cases, you've got a problem which will say use 2 T flip-flops. and then you got no choice. Or you may, look in your parts box, and all you have are D flip-flops. Well, that's what you're going to use then. And we'll see that, the type of flip-flop affects what the combinational logic looks like. And often, if we use JK flip-flops, the combinational logic comes out simpler than if we use T or we use D. But something, has to answer this question. So for our first version of this, let's just suppose we're going to use D flip-flops. And it's not because that's better, or that's the only option. It's just we've got to pick something. So we'll do our first version of this with D flip-flops. All right. So our next task is make a state transition table. Right. So the last part of our analysis goes from a table to a diagram. Here we're going to go from the diagram to a table. And so what does our table look like? Well, we have our present state, and we have our input. And we have our output. And we have our next state. And this we just fill in from the diagram. So if our present state is A and our input is a 0, then our output is a 0 and our next state is A. Right? That's just looking at this diagram. If we're in a 0 and we get a 0 coming in, our new state will be A, our output is a 0. If we're in state A and our input is 1, our output is still 0, but we go to state B. And so we can fill in all of these values. And we need to be a little careful of whether this is a Mealy or a Moore machine. In this case, it's clearly a Moore machine because my state is the only thing that determines the output. Right? My output is a 1 in state D, it's a 0 in other states. So I can write my outputs based on the present state. And it's always going to be that. And then our next state is, if you're in state B and you get a 0, we go back to A. If you've got a 1, you go to C. If you're in C and it's a 0, we go back to A. If it's a 1, we go to D. D with a 0 goes to A. D with a 1 stays in D. So that's just coding this information. All right. Well, now we've got to, and you could do this earlier rather than later, assign flip-flop values for each state. So this is the state assignment table that we started with before. So I've got states, they're called A, B, C, D. I'm going to have 2 flip-flops. So their outputs, I'm going to call those Q1 and Q0. And we have 4 combinations. And what state is going to be represented by each of those combinations? Well, I'll be unimaginative and just do that. So now I can fill in my present state in terms of Q1 and Q0. So state A is a 0, 0, B is a 0, 1, C is a 1, 0, D is a 1, 1. And my next state I can also represent as I'm going to write Q1 plus and Q0 plus, the new values of Q1 and Q0 after the clock tick. So this is a 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1, 0, 0, 1, 1. Alright, at this point, I'm done with my diagram. I don't need to refer to this anymore. I've got all of this information coded into this table. And this was really the table that we used at the end of the analysis that we said, now by looking at this, I can make a diagram. So this and this are different representations of the same information. So maybe so you don't have to squeeze in your columns here, make that state assignment first and then put that into your transition table. But you end up with a table like this. Okay, now comes the interesting part. Determine necessary flip-flop inputs. Alright, everything I've done up to here has been independent of what kinds of flip-flops I'm using. I haven't used the fact that I'm using D flip-flops yet. If I was doing JK flip-flops, this part of the analysis of the synthesis would be the same. But now we're going to say, what should we set the inputs of the flip-flops to? Well, since I'm using D flip-flops, I know a D flip-flop has a single input. And so I need an input D1 and an input D0 for those two flip-flops. Alright, so this is the reverse of the question we've been asking so far. With a D flip-flop, we can write this table. And we know, if the D input is 0, the new value of the flip-flop is going to be 0, regardless of its current value. If the D input is 1, the new value is going to be a 1. So this is the table we've been working with for D flip-flops. Based on the current value of the flip-flop and the D input, what's the new value of the flip-flop? Well, now we have to run this backwards. Our goal is, hey, if Q1 is currently a 0 and we want it to become a 0 after the clock tick, what value should we set D1 equal to? And in this case, the answer is a 0. Because if D is a 0 and Q is a 0, the new value is going to be a 0. And that's the same situation for the second row. And it's the same situation for this third row. But for the fourth row, this is saying, hey, if the flip-flop's currently outputting a 0, and we want it to output a 1, what value should we set D to? Well, it's currently outputting a 0. We want it to output a 1. We should set D equal to 1. All right, do you see what's going on here? We're looking at the current value of the flip-flop and the value that we want it to change to, and using that to decide what should the D input be. And for a D flip-flop, it's a pretty simple answer to that question. The D input should be whatever we want the new Q value to be. So this column is really just going to echo Q1 plus. If we want the output of the flip-flop to be a 0, set D to a 0. If we want the output of the flip-flop to be a 1, set D to be a 1. And then for the other flip-flop, flip-flop 0, if we want the output to be a 0, set D to a 0. If we want the output to be a 1, set D to a 1. And so this just becomes a copy of whatever the desired Q value is going to be. So this is the pivotal step. So I want to make sure everybody understands why these are the values in these columns, not simply because they match this, but what's the logic behind that? Does everybody understand why I'm setting these to these values based on all that stuff to the left? All right, so from here it's a ish is fine. We're going to do this a few more times, so once we've got these columns, this is a week 1 question now, right? Now we just write equations for the flip-flop inputs and the machine output. So now we just say, hey, here's the output I want to generate. Here's 2 flip-flop inputs I want to generate. How do you get the values of Q1 plus Q0 plus? If the next state is going to be A, I know that A corresponds to Q1 is 0, Q0 is 0. So if my new state's going to be A, I want my new Q1 to be 0, my new Q0 to be 0. If my new state is going to be B, I want my new Q1 to be 0 and my new Q0 to be 1, because B is represented by a 0, 1. So all this stuff gets set up, the clock ticks, boom, your Q's change to this, suddenly you're in state B. And so now we're over here. Cool, you're welcome. All right, so this is a truth table question, right? We have inputs Q1, Q0, and some input, X. So let me call this X and let me call this Z. All right. So we have combinations of Q1, Q0, X for inputs, and we want to figure out equations to make D1, D0, and Z match these columns. And I don't have to write this in a new table, but I can. And so my D1 is going to be 0, 0, 0, 1, 0, 1, 0, 1. D0 is going to be 0, 1, 0, 0, 0, 1, 0, 1. And Z is going to be mostly zeros. So how do I write equations for this? Well, write a sum of products, write a product of sums, whatever your favorite is. I can get rid of my state table at this point, and so I could write, D1 equals sum of 3, 5, 7. D0 equals sum of 1, 5, 7, and Z equals sum 6, 7. So there's my equations in compact form, and I can make a K-map, and I can simplify and reduce, and I can come up with, small equations for this. And so Z I can do in my head, right? Z is just equal to Q1, Q0. It's just an AND gate of those two Q inputs. D1 Q1, Q0, X. So 0, 1, 2, 3, 4, 5, 6, 7. So D1 looks like this, and I have two rectangles I can use. So D1 looks like it's going to be equal to Q1, X, or Q0, Q1X. And let's see if that's right. Q0X, Q1X, Q1X, Q0X, Q0X, yeah. And then D0, make your K map Q1, Q0X. And so D0 looks like 0, 1, 2, 3, 4, 5, 6, 7. So I can cover here, that's the same cover as before, so this is Q1X. I can also do the split cover, which is Q0 bar X. And now I've got equations, now I can sketch my circuit if I want. And what does my circuit look like? Well, I have a pair of D flip-flops, D0, D1. I know I have a Q0 and a Q0 bar coming out of each of these, and a Q1, Q1 bar coming out of these. And I have some input X, and it doesn't look like I need X bar anywhere. And so I might do something like this. If I wanted to be systematic about it. So what have I got here? This is Q1 bar, this is Q1, this top line is Q0 bar, and this is Q0. And now I've got, you know, the setup I had from knowing how to draw circuits more neatly. And so I can take Q1, Q0, use that to generate my Z. So Q1, Q0, go into an AND gate. There's my output Z. And then D0 is Q1X. So I can do Q1X. And those, I can do Q0X. And then if I OR those, looks like I'm doing D1, Q0 bar. Alright, so Q1X, Q0 bar X. And if I OR those, that should be my D0 input. And then D1 is Q1X or Q0X. So I'll do X, Q1, and I'll do X, Q0, and OR those, and that's my input D1. And if I wanted to, I could show the clock. A lot of times we don't even bother with the clock. But there's a complete schematic, and if I do an analysis on that, right, I should end up with a diagram that looks like this. So that's the whole synthesis process. And so the machine really has, you know, one input and one output. and a clock. The clock's not really considered an input. But, you know, as a state diagram, X goes in and Z goes out. And there's an implementation. So yeah, this is what you're going to do for homework 6. So let's eyeball homework 6. Oh, it's spring 22. Oh well. So I've kind of written a synopsis of this process here, right? Begin with a state diagram, decide how many flip-flops, make a state assignment table showing how the combination of flip-flop values corresponds to each state, make the present state, next state table from the diagram, add any outputs, base them on the present state, not the next state. Once you know the next state for each row, you also know what the next Q output should be, right? Add that information to your table, and then depending on the type of flip-flop, figure out what the flip-flop inputs must be to make the outputs whatever you need them to be. So add the required flip-flop inputs to the table, and then do, you know, your sum of product of sums, K-maps, magic, whatever your technique is to get equations for that truth table, right? And remember, the clock's not considered an input. But this should give you a set of equations for the flip-flop inputs in terms of the present state and any external inputs. And then you can go ahead and you can try to sketch a circuit. And when we're designing the state machine, we're not actually thinking about implementing it in Tinkercad. So we're not going to put in pin numbers. We're not going to list a 7404 when we have an inverter and put down part numbers and so on. We're thinking more along the terms of, you know, kind of a logical diagram like this. That's as far as I want you to go, unless you're trying to actually implement this. Now, if you were doing this in a lab, right, you would need to change this into a wiring diagram with, you know, part numbers on these and pin numbers on each input and output to each gate, and, you know, possibly switches and LEDs and so on. We don't need that for the homework that we're doing, right? So your goal is to, you know, show the flip-flops, the logic symbols, and the connections. And for all of the questions in this homework, we're using one diagram. So we start in state 0, 0, and if we have a 0, we go to state 0, 1. If we have a 1, we go to state 1, 0, and so on and so forth. This is a Moore machine, so your output Z only depends on your state. And so there's 3 synthesis questions. First, do this synthesis using D flip-flops. And then do it using T flip-flops, and then do it using JK flip-flops. And we'll talk about what these don't cares are about in a few minutes. And then, as I said, go ahead and pick up problem 5 from homework 5. That's just that maximum clock frequency analysis. All right, questions so far?
Yes.
Yeah.
But it's more for lab 6.
Okay.
So, when I was trying to implement it into Tinkercad, because that's where I work best, I ran into difficulties with essentially hooking it up, the flip-flops.
Mm-hmm.
I was wondering how should I hook up a D flip-flop?
Well, how are you trying to hook it up? What are you trying to get it to do?
It's the 4-second delay.
Okay.
So I have my N555 going into it,
Mm-hmm.
and the output goes back into it, but the this because it's a 2-second, so I guess another D flip-flop.
Okay.
And the output of that is what I'm trying to use.
Okay.
So, should I... Yeah.
So pin 3 of your 555 is going to the clock on these flip-flops. And then my suggestion for testing this is just put a push button on here, and on the output put an LED.
Okay.
And switch is open, LED is on. Flip that switch so it's closed, and 2 to 4 seconds later the light should go off.
Okay.
Then open the switch, 2 to 4 seconds later light should come on. And it's a nice visible delay that that's different from, you know, just hooking up an LED to an inverter or something.
Okay, perfect. Thank you.
Yeah, you're welcome. All right, well, let's suppose that instead of being asked to use D flip-flops, we were asked to use T flip-flops. So suppose we had the same state diagram, but somebody said, I want you to use toggle flip-flops, right? And we remember, you know, the behavior of a T flip-flop is like this. It depends on both the T input and the current value of the flip-flop. And so if T is 0, the flip-flop does not change. When the clock ticks, nothing happens. But if T is 1, when you tick the clock, the flip-flop toggles. So if it's currently outputting a 0, tick the clock, it outputs a 1. If it's currently outputting a 1, tick the clock, it outputs a 0. So a toggle flip-flop is different from a D flip-flop. Right? D flip-flops had this behavior of the output always matches whatever the D input is. But here, you know, the output is not always the same as the T input. The output is either the same as it was or the opposite of what it was. So if you want to design this circuit using T flip-flops, all of this is exactly the same. But now, instead of figuring out inputs for D flip-flops, we would figure out inputs for T flip-flops. And this is a little trickier, but it's exactly the same process. So suppose we just look at this first row. And we're going to ignore, you know, these D columns. We're just looking at this first row, and we're just going to look at Q1. Just look at the current value of Q1 and the new value of Q1, and let's figure out what the value of T1 should be. So we have a toggle flip-flop. It's outputting a 0, and we want it to stay at a 0 after the clock ticks. What value should we set the T input? It's currently outputting a 0. We want it to stay at a 0. What should T be? Should be a 0, exactly. Right? If it's currently at a 0 and we want it to stay at a 0, T has got to be a 0. If it's currently a 0 and we set T equal to 1, it's going to change. So if Q1 is a 0 and we want the new Q1 to be a 0, set T equal to 0. Same thing in the second row, 0, 0 should be a 0. Same thing in the third row, 0, 0 should be a 0. Okay, in this fourth row, it's currently a 0, and we want the new value to be a 1. What should we set T to? Yep, set it to a 1. It's currently a 0, and we want the new value to be a 1. Set it to a 1. All right, fifth row, it's currently a 1, and we want it to become a 0. what did we set t equal to? Currently a 1, we want it to become a 0. Yep. Right? I mean, your only options, t is either a 1 or a 0. And so we can simplify this by saying, hey, if we want q to toggle, let's set t equal to a 1. If we don't want q to toggle, it's a 1, we want it to stay a 1, we'll set t equal to 0. So now we just look at the current value of q, the new value of q. If they change, set t equal to 1. If the current value of q and the new value are the same, set t equal to 0. And then t0, we do the same thing, looking at q0 and the new value of q0. So 0, 0 will be 0, 0, 1 says toggle, 1, 0 says toggle, 1, 0 says toggle, 0, 0 don't toggle, 0, 1 toggle, 1, 0 toggle, and 1, 1 don't toggle. So we've done the exact type of analysis we just did before, but we got different output columns for T1 and T0. And so now when we write equations for these, we'll get different equations, and that'll ultimately give us a different circuit. But when we analyze that circuit, we'll get the exact same diagram that we got before, which will be, you know, that. If I'm doing a sum of products, right, well, I've got 5 1s in here, so that's unsimplified going to be a more complex term. But when I do the K-map, will this be simpler or more complex than what I had before? I don't know. I think it'll probably come out about the same. So, you know, sometimes you might analyze this process for different types of flip-flops. And it may be that, you know, for flip-flop 0, a D flip-flop is most efficient, and for flip-flop 1, a T flip-flop takes almost no logic. And I might decide to use, you know, a D flip-flop for the first one and a T flip-flop for the second one. Again, that's probably not something that's usually done because we have machines to do this for us. And when we're building a large system, it's cheaper to use one type of device than to try to mix and match to save, you know, a few random gates. But, you know, theoretically, you can analyze this for, you know, whatever type of flip-flops you want. All right, with JK flip-flops, it gets more interesting though. So let's make a copy of part of this table. So I'm just going to do Q1, Q0. And the new value of Q1 and the new value of Q0 and one input. And I'm going to skip all the other stuff. So I've done my careful analysis, and I've filled in all these columns, and here's what we've ended up with, right? And this is the part that's independent of the type of flip-flop that you have. All right. right, suppose you're told do this using JK flip-flops. So we're going to end up with, you know, some kind of machine like this, but our flip-flops are going to have, you know, a J and a K input. And down here is going to be a J and a K input. So the circuitry we're going to build is responsible for setting up the value of this J0 input and this K0 input and this J1 and K1 pair of inputs. So I'm going to have 4 columns over here. J1, K1, J0, K0. And so again, let's just look at flip-flop 1. Let's just look at Q1 and the new value of Q1 and figure out what we want our new J and K to be. Alright, well, we need to remember what a JK flip-flop does. And the usual way that we write a JK function table is like this. If J and K are 0, Q doesn't change. If JK are 0, 1, Q resets. If JK are 1, 0, Q sets. And if JK are both 1, then Q toggles. So that's the way we've described JK flip-flops. That's what you'll see in a data sheet. But we can be a little more explicit by, you know, making Q an input, and we can say if J and K are both 0 and Q is currently a 0, new value of Q is 0. If JK are 0, which means don't change the flip-flop, and Q is a 1, new value will be 1. If JK is 0, 1, it doesn't matter what the current value is, Q is going to get reset. If JK are 1, 0, it doesn't matter what the value of Q is, flip-flop will get set. And if J and K are both 1, the flip-flop will toggle. So if Q is a 0, the new Q will be 1. If Q is a 1, the new Q will be a 0. So this is what we can call a compressed truth table, right? Because the output is not just zeros and ones, it also contains this other information, Q. If we wanted to make this into a pure truth table, right, this would be our standard truth table. Here's 3 sort of inputs, and here's what the output is. So you can use whichever form resonates with you. But our goal is, you know, if we know that our flip-flop currently has a 0 and we want its new value to be a 0, what should we set J and K to? So that's an open question. My flip-flop's currently at a 0 and I want it to stay at a 0. What should I set J and K equal to? So first row, I want to go from a 0 to a 0. Set it to a 0 and a 1. Right? Why? Because if I set J to 0 and K to 1, my flip-flop's going to go to a 0. Is there a second answer that would also work? Is there any other combinations of inputs that would cause my output to go to a 0? Zero and 0. Because if J and K are 0, and my current value of Q is 0, my new value of Q will also be 0. So 0, 1 is the input combination that says, hey, force the output to a 0. That's definitely going to get me where I want. But 0, 0 is an input combination that says, hey, don't change the flip-flop value. Well, since the flip-flop is already a 0, if I say don't change it, it's still going to be a 0. So I could do a 0, 1, or I could do a 0, 0. And both of those will get me what I want. So I could put an X in for that case. So 0, 1 or 0, 0. This means I have to set J to a 0, but I don't care what I set K to. Alright, so this is really, really important and really useful. Because remember, when you have a truth table and you have don't cares, when you make a K-map, those don't cares are optional covers. You're allowed to cover them if it helps you. You're allowed to ignore them if you'd rather ignore them. So having don't cares in your table will generally lead to simpler equations, which means a simpler circuit diagram and an easier implementation. Alright, so we can copy this anywhere we're going from a 0 to a 0. Set J to a 0, K to a don't care. Here's another 0, 0. And I think that's it for 0, 0s. Okay, let's look at this fourth row. We've currently got an output of 0. We want our new output to be a 1. So we're going from a 0 to a 1. What should we set J and K to? So if we set it to 0, 1, let's see. Actually, not quite 0, 1. 0, 1 is going to force the output to a 0, but we want the output to become a 1. So 1, 0 will work. Because if our inputs are 1, 0, the new output of the flip-flop is going to be a 1. That's what we're after. And then is there another possibility for that? Let me move this previous one up. Is there a different way to go from a 0 to a 1? So currently a 0, we want to become a 1. 1, 1, perfect. Because if our inputs are both 1, that says, hey, the flip-flop should change its value. Well, if the flip-flop's currently a 0 and our inputs are 1, 1, when we toggle that 0, it'll become a 1. So we could also do a 1, 1 or a 1, 0. Conclusion, the J has to be a 1, but the K does not matter. So here we could say set J equal to 1. I don't care what you set K to. Right? If K happens to be a 0, well 1, 0 says, hey, output should become a 1. That's correct. If K happens to be a 1, 1, 1 says, hey, toggle the output. Well, the output's currently a 0. When it toggles, it'll be a 1. That's still the right thing. So as long as J is 1, we don't care what K is equal to. Alright, two more categories. Currently a 1, want to become a 0. So we want Q to be a 1, and we want Q plus to be a 0. So what should we set J and K equal to? Right, so 1, 1, because 1, 1 says toggle the output. And also 0, 1, because 0, 1 says clear the output. So here we so 1 0, we said we could do 1 1, or we could do write it like this, or we could do 0 1 because that says clear the output. So this is a 1 1 or a 0 1. So J doesn't matter as long as K is equal to 1. So this is a don't care followed by a 1. And we can replicate that down here because it's the same situation. We're currently outputting a 1. We want to output a 0. So this should be a don't care 1. And then our last situation, Q is a 1, and we want the new value of Q to be a 1. And so what should we set J and K equal to have our flip-flop go from a 1 to a 1? Yep, 0 0 says don't change, and 1 0 says set the output to a 1. And so here we don't care what J is, and K has to be a 0. So this is a don't care 0, this is a don't care 0. Well, when I do my K-map analysis, this is going to be glorious, right? I can eyeball this, and I can say, hey, if I set J1 equal to Q0 ANDed with X, right? This is going to give me a 1 right here. It's going to give me 0, 0, 0, 1. Well, I don't care what these values are. They can be anything. All I got to do is make sure I get a 1 in this one particular row. And in this row, I can just say, hey, just take Q0 and AND it with X. So J1 is just going to be an AND gate. Going to take the output of Q from the first flip-flop, AND it with the input X. And K1, I'm just going to set that to the inverse of X. If X is 0, K1 will be equal to 1. And if X is 1, K1 will be equal to 0. So I'll just take my input X, run it through an inverter, hook that up to K1. Super simple logic, right? And then J0, K0, I'm going to do exactly the same thing we just did, but I'm going to look at the current value of Q0 and the new value of Q0. All right, that's the whole synthesis process. So there are examples in the textbook that take you through this, and then there's some examples in the textbook that you know, propose questions but don't give you the answers. And then in the unassigned homework set that you can find on ENGRCS.com, well, let me show you where that is, if you haven't found this already. So if you go to course syllabi and engineering 250, this is where some of those homework assignments are coming from. And so sequential circuit design. So if you look at this chapter 5 homework, there's a bunch of questions here on designing state machines. And as usual, there's, you know, a solved version of a question, and then there's a similar question which is unsolved. And so you can practice by, you know, looking at the solved question, coming up with your solutions, and then comparing it to the solution that's worked out here. And then you can challenge yourself more by tackling the unsolved question, and so on. Right? But these aren't the questions you're going to turn in. These are just more questions you can use to practice these concepts. But it's you know, building a present state, next state table, figuring out what your flip-flop inputs should be, writing equations, simplifying them, sketching a schematic. So there's plenty of material to work through to get better practice with this this notion of machine synthesis. So my suggestion would be, you know, get started on the homework. If you have time today, that would be awesome, because then you can come to lab hours tonight. If not, start on it as soon as possible. Come to office hours on Thursday or Friday. And, worst case, well, not worst case, but, if none of those work, try to finish the homework by Monday so that you can ask questions in class on Monday. And if there's still questions after that, there's still office hours Tuesday, and there's still lab hours next Wednesday, and the homework's due at midnight. So there's plenty of opportunity there, right? But the sooner you start, the better. You know, understanding you have to juggle this with other classes. But you really don't want to start this, next Wednesday. So on a good day, doing one of these questions will take, 15 or 20 minutes once you understand the process and you can work through it flawlessly. If it's the first time you're doing this, it might take you an hour or more to do, one of these problems. And the more you do it, the quicker it will become, because the more you'll understand kind of at a conceptual level what's going on, why you're doing these things. You don't want this to be a mechanical process, though. There's no benefit in just sort of memorizing a set of steps or finding a checklist online that says, if it's JK, then just fill in these numbers and so on. I want you to understand why, each of these steps takes place and how this is, basically doing the reverse of the analysis situation. All right, we've got a few minutes left. Let me talk about other encodings, because there's this question of how many flip-flops do we want to use, and if we've got 4 states, we know that 2 flip-flops is sufficient. But it may be that we decide to use a different number of flip-flops. So for example, we have 4 states, A, B, C, D. What if we had 3 flip-flops? Or 4 flip-flops? And we said state A is represented by 0, 0, 0, 1. State B looks like this, state C looks like this, and state D looks like that. And any other combination of flip-flops is an invalid state. So this is called one-hot encoding. And hot is a synonymous term with an output being 1, or active, right? So one-hot encoding means that if we look at the state of our flip-flops, exactly one of them should be turned on to a 1 at any point. And all the others should be off at a state of 0. And this is not an uncommon way to code states inside a state machine, to use 4 flip-flops to represent 4 states. And the reason we do this has to do with glitches. So with our fully encoded, so this is one hot, this is fully encoded. Right, here's the situation. Suppose state D is some kind of emergency state. And we have a more output which says, as soon as we're in state D, turn on the alarm, right, and wake everybody in the building up. And maybe this is a temperature control system, and so state A is the startup, and state B is heating, and state C is cooling, and state D is some kind of, catastrophic failure. So this is init, this is heat, this is cool, this is, get out of the building. Well, so the system, you turn it on, it starts in state 0. Now it's just moving from state 0, 1 to state 1, 0 to 0, 1, and so on. It's just going between heating and cooling, right? But, imperfect circuits, our flip-flops may not change exactly from 0, 1 to 1, 0. It may be that if our flip-flop outputs are 0, 1, and we're moving to state 1, 0, well, maybe flip-flop Q1 turns on first, and then shortly after, flip-flop Q0 changes to a 0. but in between there was this brief moment when both flip-flops were on. And if we have logic in our circuit that says, hey, if Q1 and Q0 are both 1, turn on the alarm, well, during this brief instant, the alarm went on. And if our circuit is set up so that once the alarm goes on, it stays on until somebody comes in with a key and turns it off, well, we just woke up the whole building as we moved from, a heating cycle to a cooling cycle. So if we coded our system like this, and we were moving from state B to state C, well, there's state B, here's state C. Maybe in between those two, we would have this temporary state, but this is not a valid state. And we would design our system so that if you're in a state other than one of these 4 encodings, it's a no-op. Nothing happens. And so we're in our heating state, we go to this illegal state, and then we come to the cooling state. And there's nowhere in this transition that we're ever going to come into this emergency state. And so one hot encoding is useful sometimes to help deal with potential glitches. Glitches in the form of transitory transitions from one state to another, right? Transitory intermediate states. So that's something that you'll see. The design process is exactly the same though, right? The only difference would be that we would have a different coding of our flip-flops for each state. And so in this case we'd have 4 flip-flops, Q3, 2, 1, and 0. We'd have 4 next states, Q3, 2, 1, and 0 plus. And if these were D flip-flops, we'd have 4 D inputs we'd have to generate, D3, 2, 1, and 0. But the process is exactly the same. So I think the book has some questions that deal with one hot encoding, and you can read about those and try those if you like. All right, we are out of time. That's plenty of stuff to chew on. Monday we can talk about questions obviously on either the lab or the homework or anything related to these concepts. I'll pick up a few other topics that have come up along the way that we haven't gotten to. And then we're going to jump into the last unit of this course, which is hardware definition languages. We're going to play with something called Verilog. And so I'll post some instructions on Canvas over the next couple of days for some software to download that you're going to want to use for this last part of the course. So I'll post some download instructions for that in an announcement, so look for that. And we'll start talking about that Monday. All right, that's all I got. Have a great rest of the week, great weekend. I'll see everyone next time. Thank you.